Hi, this is Mrs. Poland again with the second video on the chi-square goodness of fit test with example 2. Offspring of certain fruit flies may have yellow or ebony bodies, normal wings or short wings. Genetic theory predicts that these traits will appear in the ratio of 9:3 to 3:1. Yellow and normal, yellow and short, ebony and normal, and ebony and short. A researcher checks 100 such flies and finds that the distribution of traits are 59, 20, 11, and 10. And although the problem is broken up differently, I'd like to just treat this as a regular hypothesis test problem. So we'll kind of get all those answers together in one. So when we recognize that this is a chi-square goodness of fit test because we're dealing with categorical data based on these four categories. And we're dealing with more than one category, so you couldn't do a two-proportion test. You would have no choice but to evaluate it with some sort of chi-square test. I know it's a chi-square distribution test because we're comparing these observed counts to a theoretical ratio. So I start off by defining my null and my alternative hypothesis. The claimed distribution of traits is true. In other words, it's in a 9:3 to 3:1 ratio. The alternative hypothesis is the claimed distribution of traits is not true. Next, we talk about the conditions. So theoretically, we should know if the flies were randomly selected. And since we weren't told, we're going to say random sample assumed. We also need to follow the 10% condition. It is reasonable to assume that there are more than 1,000 flies in the population. And the third condition is the expected count condition. All of the expected pounds have to be greater than or equal to 5. And you may not have gotten that from that first example that I showed you, though it certainly was the case in the M&M case. So how do I calculate the expected count? The first thing you need to do is set up a table. So you're going to have the observed count and the expected count. And in this case, there were actually 4 categories. There was yellow and normal wing, yellow and short wings, ebony and normal wings, and ebony and short wings. And the observed count, we could go back to the original problem, was 59, 20, 11, and 11. And I'm just following this order over here. So if you add that up, that should add to 100. For the expected count, we're not given percentages, but we're given a ratio. And so we can, again, calculate it out. There are many ways to do it. One way of doing it is just to make a tiny little algebraic equation. We know the total count has to equal to 100. So this is 16x is equal to 100. X is equal to 100 over 16, which equals 6.25. I'm not even going to round. So this is a ratio of 9x, 3x, 3x, and x. So 9 times 6.25 turns out to be 56.25. 3 times 6.25 is 18.75. This is going to be the same. And this is going to be 6.25. It's not really necessary to round in this case since the numbers are fairly easy to work with. And that equals to 100. So notice all these counts are greater than or equal to 5. It's the expected counts that have to be greater than or equal to 5. So you need to say that. You're now going to say all conditions have been met. Therefore, we can perform a chi-squared goodness of fit test. Goodness of fit test. You can abbreviate goodness of fit test as the chi-squared capital G OF test. And the degrees of freedom or the category is -1. So in this case, the degrees of freedom are 4 minus 1 or 3. Okay, we're now ready for the calculations. Maybe I'll switch colors. So the chi-squared formula is the summation of the observed minus the expected squared over the expected. That formula is given to you on your formula sheet. So in this case, there are 4 components since there are 4 categories. And we don't have to set it up as a chart like we did with the M&Ms. So it would be 59 minus 56.25 squared over the other expected. That's for yellow normal. Then you're going to do 20 minus 18.75 squared divided by 18.75. The third is 11 minus 18.75 squared over 18.75. And finally, the last is 11 minus 6.25 squared over 6.25. Tomorrow I'll show you an easier way of doing the calculations, but for today I do want you to do it by hand. And when you enter this into the calculator, the first component is 0.134. When you enter this second expression into the calculator, you get a value of 0.083. When you enter that third component into the calculator, and you should just check my arithmetic, you get 3.203. And when you enter the third component into the calculator, you get 2.25. You're going to then add up those total components, all 4 of them, and you get a value of 5.67. You now need to determine if this is statistically significant. So the chi-squared distribution is right skewed, and here's 5.67. I'm not going to show you how you can calculate it with the table today. I'm only going to use the calculator. So we want to find out the chance that I get a statistic, chi-squared statistic of 5.67 or higher. So this is going to be our p-value, and it's the probability our chi-squared test statistic is greater than 5.67, and you're going to use the chi-squared distribution, CDF. The low is 5.67, the high is 9E999, and the degrees of freedom again is 4 minus 1 or 3. We go to our calculator again in our calculator menu, and we hit menu, statistics, distributions, chi-squared CDF. The low is 5.67. The high is 9 E999, and the degrees of freedom is 3. And I hit OK. And I get 0.1288. Oh, I should have in the beginning defined my significance level. I'm going to just use standard, but again, that should be defined before you start any kind of analysis. And now I'm going to write my conclusion. So since the p-value is greater than 0.05, we failed to reject HL. We do not have convincing evidence that the distribution of traits is different from the original claim of 9 to 3 to 3 to 1.